Okay, and I hope for international students, I hope you come to Taiwan maybe before middle of December, because I think in the middle of December the border will be closed because of the it will be nearby Chinese New Year, so you need to come before middle of December, or else you will come next year, maybe February, around February. Okay. And for the overseas students, have you arrived at Taiwan? Okay. Quarantine. Okay. Who else still quarantine? Only Rion, or how about Afando and Jonathan? You already here, right? Or still? Yeah. Oh, Tuan, you already here also. How about Afando? You still outside or already in Taiwan? Oh, you guys December, right? You guys December, right? Ah, December 16. December 16 is arriving at Taiwan or arriving at the campus? Oh, okay, okay. That's okay. Okay. Okay, good, Jonathan. Okay, let me start the course. Okay. Let me start from the feedback. Okay, the feedback. You have you are given this graph. Okay, and first look carefully here. The graph is showing the f prime. Okay, so this important. Okay? So this is uh, f prime, not f. Okay, that's the key. The question is asking what values of x does f have for a local max. Local max. Okay, remember. Okay, the idea of local max and local mean is if you have positive gradient, positive slope, and then it's changed to negative slope. So this point here will be max, right? If you have slope negative and becomes positive, then this point here will be your minimum, right? Your minimum or local minimum. So we need to find when the slope is changing from positive, okay? And here maybe it's 0 and then negative, right? Here also negative, 0, and then positive. If you look at the graph, okay, if you are not carefully read the questions, maybe you are thinking the local max is here and here, right? But this is actually f prime. So f prime means this y whole y here is positive. This whole y here is positive. So this will be positive, right? This is positive area. And this will be negative area. The bottom one is negative area. Okay. So the y-axis is our f prime. Okay. So we are looking at when the positive change to negative or crossing the x-axis, right? So if we look here, the first one here, at x equal 1, if you see, that is from negative to positive. This is minimum. So x equal 1 is minimum. If you look at 6, it's from positive to negative. So that's our max value. And this 8, x equal 8, from negative to positive, another minimum. So the maximum will be at x equals 6, okay? At x equals 6. So at x equals 6, this will be, you can write, we can have local max. Okay, yeah. It happens, okay, because we didn't carefully read the description. So now we can have, okay, so first you can have the f prime, and also f with double prime, the second derivative. We can also make the graph, okay? And then you need to carefully think about that. If it's talking about f prime, meaning we are talking about maximum and minimum, mostly about that aspect. If second derivative, we are talking about concavity. Okay. So if let me write here just to remind you. So f prime, we can have observe f increasing or decreasing, and from here we can get uh, or we can look at the local max and local min. And for the double prime, the second derivative, we can have concavity. Concavity is if I draw the graphs like this or like this. Okay? This one is if the double prime is positive. This if double prime is negative. Okay. And whenever you find f prime equals 0, this will be your critical number. And f double prime equals 0, this will be your inflection point. Okay. So as long as you understand the concept, okay, not really the definition on how the theorem will be, as long as you understand from the graph how you visualize and then get the conclusions about the first derivative and second derivative, I think it's still good for you, okay, to move on to sketch the graph using calculus, okay, by using just this two point, f prime and f double prime. At least you can sketch the graph roughly. Okay, that's the first question in the feedback, our feedback. Okay, now the next question is this, right? Okay, now we are looking at, let me erase this part first. If we're looking at this, and the function is just asking the local max is at which x value and local min at which value, and please write in the form of AB. I already prepared to have bracket or none. If you forget to write bracket, does it still correct? Okay. Okay. Now let's check from our function here. Okay. We have x squared divide x minus 1. Okay. Okay. If you'd like, okay, you can also, okay, sometimes if you want to draw, yes, if you want to draw, you can write this. So divide first. If you want to write in another form, so we'll have a remainder here. So this will be also equal with x plus 1, and then plus 1 x minus 1. Okay. Now, this is another way to get our function. Sometimes this can be helpful. Okay? If you think this is too difficult, if you want to derive, and you maybe feels let me show you. If you feels that this squared makes trouble in your calculation, you can do expand, become this. Okay, still doable. Okay, still doable. Okay, and from here you can also look at this. Okay, I haven't told you before here. This x plus 1 here. This is also asymptote. Okay, asymptote, but it's not vertical, not horizontal. We call this a slant asymptote. We call slant asymptote. So the asymptote has a linear equation. So it will be like this or maybe like this, okay, the slant asymptote. How to get slant asymptote? Okay. First, the the numerator and denominator, the difference should be at least 1. This should be 1 higher than the bottom. Okay, so this x squared x, or maybe you have x cubed and then x squared. You can have also a slant asymptote. So this needs to be a linear equation. So that's why it's a linear. So the difference should be at least 1 degree difference. Okay. So if you would like to draw, okay, let me draw in another. And you want to check with maybe a graphing calculator how the graph will be. The graph will be, if you check, if you use your smartphone, I think there is an app for graphing calculator, and it is useful, especially if you are maybe working some homework or maybe assignment related to graphing calculator. I suggest you to check it, okay, and try. If you want to draw, let me just draw first, okay. The draw is probably like this. It will be like this, and it will have asymptote at 1, right? It has asymptote like this, and it has maybe this is 4. Let me make this smaller first. Let me resize first so that I can make it. Yeah. Okay. You will see if you check with your graphing calculator, you will see that first we will have 1 here, vertical asymptote. That vertical asymptote is from here, x minus 1. So x should not be equal 1. And you check with limit for asymptote. I will get back to that later. Next part, okay, I will explain in details. But here is, you can see that there will be asymptote. If you check with the graphing calculator, you will get this asymptote. And this x plus 1 is here. Okay, that's how you get the slant asymptote. So if you want to draw the graph really detailed, you can get this expression and you can make it into functions. Okay, so you can get this and the rest of the details. We are using our calculus information. I will get back into that information later. Okay, this is just for brief introductions first. Okay, so if I draw the line, it should be having this line here. This the slant asymptote. So this is y equal x plus 1. Okay. Oh, also, another way to help you study. Okay. So aside from checking the graph in GeoGebra or any graphing calculator, so GeoGebra, you can also use the Wolfram Alpha. Maybe I will make another video on how you can use this tool website for learning any problem in mathematics or in calculus on your own. Okay? And it's really helpful. Also, if I forget something and I want to get the answer really quick, I go to these two websites. Okay. So Wolfram Alpha is basically, it's a robot. It's how to say that? Yeah, it's a robot. So we are asking questions from this Wolfram Alpha. The topics can be anything, any topics: science, technology, social, culture, also mathematics. So if you use Wolfram Alpha, you can get some directions. For example, we are still in derivative. If you have some complicated derivative, you can ask Wolfram Alpha. For example, if you want to ask, maybe asking ln x, what is the derivative of this? What we can do, Okay, we can write in Wolfram alpha derivative of, you write with bracket ln x, and then with the, say that, we can write derivative of, and then write this apostrophe, and then write cos x. And now I think the Wolfram alpha has a symbols for calculator, so it's really, really nice, really neat, and it's really helpful. But sometimes, because it's a computer, the results may be a little bit different if you calculate by yourself. But mostly that is because the computer has different form of math. But actually, that's the same thing. Okay. 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 So check of GeoGebra, check Wolfram alpha. Okay. I will show you maybe later with some video. Okay, back to the question here. Okay. Okay. Now the idea here, okay, to find the max and min. If the question not giving you any domain, any interval, so that means you can just assume the domain is, if you look at this, the domain will be x not equal 1, right? So all x is real number, but x should not be 1. Okay, that's the domain. So we can continue to finding the first derivative. Okay, you can use the quotient rule like this. Okay, or if you want to go to here also, you can go. The result will be the same. Okay, and you need to equaling the first derivative to 0, okay, to find the critical number. Okay, critical number. And then you have this x0 and x2. Okay, x equals 0 and x equals 2. Draw in line number. To see how the 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 x will be, and check all the x. Okay, check whether f prime is positive or f prime is negative, and we get that actually the max value is at x equals 0. Okay, from positive to negative here. So this is max, and this is min, right? So max value will be 0, and min value will be 2. So this is correct. Okay, any question first? Any question first? Let me just stop for a while. Any questions first? Some details about the asymptote, about the how to sketch the curve, I will explain later. That is our today's topic, okay? How to sketch the curve. And I know probably you are wondering, I also wonder, like maybe when I was also study in maybe high school, and I feel that from elementary, junior high, and then high school, senior high, mathematics becomes more complex, right? When you are little, or maybe you are in the elementary, you just learn how to 1 plus 3 or 4, and then you learn how to group, like you have 5 apples, 4 oranges, and then you can have, it's actually a variables like 4x plus 3y and other. Wait. Wait. Okay. 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 So from elementary school, junior high, senior high, math become complicated, and I also think back in the days, oh, it's so difficult. How and why we need to learn this, and because I see that not everyone will be doing or using math in work, right? But then when I study, and see some speech from some professor, some uh, even YouTube video, like actually mathematics, like in the 16th century, like when the calculus is born, and before that, mathematics is like uh, have the algebra, right? Yeah, like for example, let f of x is equal blah blah blah, and then you prove the formula blah 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 blah, and then you get conclusions, or that is proven, that is correct, the formula is correct. Before that is invented, how math is written is like when you write a novel, like a poem. So in Italy or in Europe or even in the Middle East, when the science already in like you have a book like a poetry, but it's actually about mathematics. So that's it's actually interesting. That's actually interesting. So people back then doesn't think math is like nowadays, like oh it's exact, or it should be an exact science. It should be having an exact result, blah blah blah. But back then people want to understand the world, and they want to connect with the world, and they are using something called mathematics, something called notations, and from there will be another branch like physics and so on and so forth, and then until now and until today. So I think the more you learn, maybe someday you will maybe uh, take some conclusion that okay, I think this is math, okay, and then maybe you can see the beauty within the mathematics. Okay. Okay. Anyway. Okay. Anyway, congratulations. Is the student here? 46 student here? No, in the classroom or online, right? Okay. Yeah. Congratulations. Okay. And statement for our course. Okay, I think more practice. Okay, I think this week I can give you some, not really an assignment, maybe just like last time. I'm just giving you some problem that you can work. And if you think that you need help from me, you can ask me through email. Okay. Some students really ask me like how to solve this, and that. Okay. 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 Last week we arrived at here, right? And we see that we need to have another way to see this two graph. Okay, if you just look at the f prime, both are positive, first derivative, slope positive. So we need to have uh, another definition. We call it's the concavity. Okay, concavity. So concavity will have, if you look the definitions, okay, it's a little bit having some words here. If the graph of f lies above all of its tangents on an interval, then f is called concave upward. If the graph of f lies below all of its tangents, f is called concave downward. So what does it mean? So I think it's better just to see from the picture. If you look here, it's called concave upward. Why? Because the graph, this is the blue line, right? The graph. The tangent is here, here. If you look closely, there is a gap here, right? There's a gap. There's a gap in between the curve and the tangent. If the curve above the tangent in all case here, we call on this interval here, it's concave upward. That's basically the definition of concave upward. And if you see this one here, okay, tangent, 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 the yellow line, okay, you have like a gap also, and the yellow line is above. Right? Now we call this concave downward, or simply upward and downward is just like you have like a bowl. Okay, if you have like this bowl here, you call upward. If you have bowl closing down like this downward. Okay. Okay. Some books using concave convex, but I think that's for me it's difficult to distinguish. I think upward and downward is better. Okay. So this will be concave upward. This is concave upward. This is concave downward. Okay. Okay, that's the definitions for concavity. So from here, you will see. Okay, you will see. We can define for some interval from A, B, C, D until some point there. We can define which one is concave downward. Oh, concave downward, and then concave upward. From here is slightly changed, right? Slightly changed, a little bit changing here, and going there. So probably in B, we will have the second derivative is 0, or we call this inflection point. Inflection point. And also in C, you get upward and then going back to downward here. Okay. Or if you want to make maybe more clear, you can use an arrow like this is going down like that, and because it's going down, we call it downward, right? I think I'm not sure how many percent of the students or of people prefer visuals rather than words. For me, visuals can be more than words. I think I can understand more clearly from visual. Sometimes when I read the definition with words, blah 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 blah, I think I feel sometimes confused. But I draw the graph. I think it's better picture to learn. Okay, so you can see this is going down, and then from here from B it's going up, and we call it upward. Okay. Okay, and then it's going down. And it's going up. But now, at this point D, we know that it's not differentiable, right? It's not differentiable, it's having a corner, okay? And also here, it's also not differentiable, but it's upwards and then still upwards, okay? And then it's changing downward, okay? Okay. All right. Yeah, I think we can go to some conclusions, some important points that you need to taken care of, and then we can have practice some example how to sketch the graph from a perspective of calculus. Okay, maybe a little bit review what we have learned before. Okay, this is just conclusions. what concavity means. Okay, so if concavity positive, concave upwards. If concavity is negative, it's concave downward. So if second derivative positive, second derivative negative. And then you will have a point called inflection point. And the function needs to be continuous. And the curve change from concave upwards to concave downward. That's the key. If you see any change, that will be the inflection point. And also from downward to upward. And suppose f double prime is continuous, you can also use the second derivative to get the local minimum or local maximum. Okay, so if you have f prime is, you know that is 0, and if you want to know directly which maximum or minimum, you can go check the f double prime. If it is positive, then it's local minimum. If it is a negative, then it will be local max. You can also use this way. Okay, and how to get the logic? Okay, how to get the logic? Maybe sometimes when we are doing exam or trouble you calculate something, and then you feel like which one is, if you don't know this min or max, you feel, oh, which one is max. You need to just draw the concavity. If you remember the concavity, this concavity will be like this. Okay, the other one will be like this. This is upwards, right? This is downwards. And you see from the picture, okay, we know that this will be mean, this will be max, right? Okay. So I think it's good if you uh, make a picture as your reference. Okay? So I think it should be more clear. Okay, that's second derivative test, and then okay, I will give you the conclusions for the sketching curve. Okay. Okay, before I give you which points that is necessary, let me just give you some example easy functions. A cubic uh, asking find max, mean, and concavity. Also inflection point. Okay, we start with simple functions first. Okay, we know that if you want to directly use this first and second derivative, we get f prime x is 3x squared minus 2x. Okay. And the double or second derivative will be 6x minus 2. Okay. Now we can find from here that is the critical numbers. So critical numbers is you need to equal with 0. So you will get x, 3x minus 2. And you will get 1x is 0. and the other one is x equal 2/3. Okay, if you want to be more careful, you can check with the line number. This is 0 and 2/3, and check all the point that is necessary. Check maybe -1, it will be positive here. If you check 1, it will be also positive, so positive here, and between 0 and 2/3, we can check maybe 1/3. 1/3, it's become positive, negative, so it should be negative here. From here, we can see that this is going up, going down, going down, going up, so this will be max, this will be min. Okay. Or local max, local min, that is also okay. Okay. For the second derivative, we can check when the f double prime is equal 0, then we have 6x negative 2 equals 0, so x will be 1/3, right? So probably this 1/3 here will be our inflection point, but we can check with some number. We can check with number, start from 0, so this will be negative, the left part negative, okay? The right part we can check with 1, 2, I think that will be positive. So this will be concave downwards, this is concave upwards, right? And this 1/3 will be our inflection point. I will write I dot P, inflection point. Okay, now how to graph the curve? Okay, you want to graph, maybe we can sketch first the axis, sketch Y, sketch X. And then you see necessary point, let's say X is 0, and then let's say this is 1. So we will have 1/3 here, 2/3 here. Okay, now before we are going to include all these calculus calculations, look at the functions first, okay? Is there any intercepts? Okay, so we can take, or we can check how many roots will be from here. So we can check this is x minus 1, this is equal 0. So x will crossing at least x equals 0 and x equal 1. It will touch the x-axis, right? You will see the roots. So when x is 0, the function is 0, so it should be having, and 0 is maximum, local maximum. So you can think it should be around like this. Okay. Right. And maybe it's from down here, and you can check also another point to help you, but at least from 0, and then you will have minimum at 2/3. 2/3 is here, so it should be like this, and it should be crossing this one, right? And now we need to draw the inflection point at this 1/3. So this should be this upwards here, and then this part is downwards. Okay. So at least you get this. Or if you have trouble with your with your drawing, that's okay, as long as you mention that this will be at x 1/3 inflection point. At x equal to over 3, this is a local minimum. And at x equals 0, this will be local maximum. Okay. I think that is all the necessary points for this function. It's not really complicated, the functions, but since we will have more and more a little bit complicated functions, we need to also think how to graph from that function. For example, like a rational function, maybe you have functions, divide functions like maybe x squared plus 2 divided by x minus 4, or any other example similar to that, then we need to be more careful. All right. And of course, this is, I'm a little bit changing the scale. One is here, right? So probably if you look at the graphing calculator, it will be much more thinner, maybe like that. Okay. Okay. Any question from here? I think this is just a simple example on how you look at the max value, mean value, and connecting all this with the inflection point concavity. Okay, you can write that from here, this point here, you can write this is concavity from this interval. Its concavity is concave downward, or the concavity is negative, or f double prime is less than 0. Okay. Now, of course, if the functions may be a little bit complicated, then we need to have some certain procedure or some process. Okay, some process. Okay. Okay, let me continue, and let me make the conclusion first. Okay. So it's for the curve sketching in general. Okay, it's curve sketching. So first, think about domain. Okay, think about domain. Think about domain. Second, think about the intercept, both x and y. So this means what happened when x is 0, what happened when the function is 0. Can you find the intercept? Can you find maybe the roots, like previous graph? There is a curve that's crossing x. Can you find that? Okay. And third is symmetry. Uh, Symmetry. So, so you can consider also if the function is symmetry or not symmetry or asymmetrical. Okay. And how to check? One way to check, or most of the time, is we can check with the minus x. We use minus x to check. If the functions give you, or coming back to the original equations, this means it's called even, right? Even function. If when we plug in negative x, if the result changing to negative f of x, then this is odd. Okay, from even and odd, you will know that if you have even, this will be precisely symmetrical. If it is odd, it's probably like this. If you imagine the cube, it's asymmetry, right? Okay. Even function, odd function. And then the fourth, so domain, intercept, symmetry, and then you can think about asymptotes. And how to find the asymptote? We are back using limit. Right? For vertical, horizontal, we are using limit. So check first limit as x approach infinity of functions. If this is resulting some finite number L, then this will be, or uh, y equal L will be the horizontal asymptote. And then if you have limit, and then your x approaching A from the left or from the right, okay? This is also from the positive or negative. Okay, this is also, you can do that also as well. This is equal with infinity or maybe negative infinity. Okay. Okay. We call this x equal A is our vertical. Okay. And at the beginning of the class, I tell you that there might be another asymptote besides the horizontal and vertical, that is a slant asymptote. That basically, if you have a polynomial, if you can make out from this some mx plus b, something like this linear, and plus this remainder here, maybe not r, maybe this is having another, let's say gx, let's say hx. Okay, I just want to focus on this mx plus b. This is called this slant asymptote. Okay, so maybe the graph like having like this and then like this, and you see that there is actually something in between. Okay, something in between like that. So you will see that the curve, okay, the curve is slightly closer to this line. And also, you need to keep in mind that asymptote is not necessarily that the line never cross asymptote. It can cross at certain point. For example, uh, uh, if you see this is going from left from right, maybe if you just see from the left, maybe it's true, and maybe from the right, maybe you can see some crossing the area. For example, this part here, or maybe the if you look at the trigonometric, you have this, right? Something that is oscillating. You can say that probably it will having something here that is like a line, okay, that it's getting closer to some line here, okay. And also here, this slant asymptote, maybe if you look in another way, maybe sometimes it's crossing, but the other way, it's never touched, okay. Sometimes you can see from both cases, okay. So that is the idea. Okay, so domain intercepts symmetry, asymptote, and then the number 5 is increasing or decreasing interval. Okay. So we need to find when the function increase, when the function decrease through the erase this, through the f prime test, the first derivative test. So check whether it's having positive or negative. Okay. And then local max and local min. Basically, this is checking the critical number. One way is to check critical number first, and then check the interval, and checking the point. You have this will be minimum, this will be maximum. Okay, and then after local max, local min, check the concavity and inflection point. Concavity we can check through second derivative. This will be concave upwards, and this will be concave downward. And if you see any change to get CU to CD or CD to CU, that is inflection point. Or you can directly write F double prime equals 0. Usually, this will be the inflection point, but not always the case. Not always the case, but most of the time, this will be the inflection point. And then try to roughly sketch a graph. And concave upward is like this, concave downward is like this. If you don't mind, let me write something regarding the Slant asymptote, because I think it's better to write here before I forget the information. Okay. So regarding the Slant asymptote, okay, and let me draw maybe like having like that. Okay, so you have this. It should be closer like that. Okay. And getting maybe closer and closer, closer. Okay. This red line is mx plus b. The curve is here. The definition of slant asymptote exactly is if x approaching infinity from here, of the difference of a function f and the linear equation mx plus b, it should be, the limit should be 0. That's the definition. The exact definition of slant asymptote. But how to find the slant asymptote is basically using the if you have, usually it's rational functions, and you need to find, for example, x squared plus x minus 1. If this is your function here, then we can find the slant asymptote. We divide the x squared plus x minus 1. Define, or you can use the polynomial division. Let me show you 1, 1, negative 1. So it should be having a reminder here. Then we have x plus 2. Oh, it's not minus, right? It's plus. Plus 1 divided by x minus 1. And this will be this slant asymptote. And again, most of the case, okay, or some requirement that you need to take is this, the numerator and the denominator should be, the difference should be 1 degree. Okay, it's x squared. This is just x. So you will know that when you divide, of course, you will have a linear equation here, right? Okay. And every time you see a function that has at least 1 degree, you need to think of there will be a slant asymptote. Okay? I need to write this slant asymptote, and then if you want to sketch the curve, then you need to write the slant asymptote in your graph. Okay. I hope this you remember. Okay. This polynomial synthetic, it's called, I'm not sure what's the name, but it's called synthetic. Okay, this x squared, x constant, divided by x minus 1 or x equal 1. Okay, so this is 1. So 1, 1, multiply here, 1, it's plus 1 plus 1, 2, multiply here, 2, plus it's 1. If this number here, we call this reminder. Or if this is 0, then it's completely divided. Okay. If you forget this, then you can just divide using just regular divisions. Just divide like that, an x and blah blah blah, blah. Right? Okay. Okay, now from here let me go through an example. Okay, maybe one or two example. Maybe one example first. Okay, sketch the curve y equal or f of x equal 2x squared divided by x squared minus 1. So because it's the same degree, so there will be no slant asymptote, right? So we can check the other asymptote if you have. Okay, for online students, you can also check. Okay, and maybe check uh, the derivative, check the asymptote, check the concavity. Okay, and I hope you understand the graph. Okay. Okay, let me give you maybe 4 to 5 minutes to try. So to start with, you can start with from any point you like. You want to find the first derivative first, or maybe finding asymptote first. Okay, as long as at the end you can sketch the curve and maybe mentioning which are the important points from the curve. Okay, I think next Thursday we're still giving you an example and maybe some important or necessary functions. And if we have time, we can go to next section. The next section is actually the Lopital Rule. Okay. I think probably most of you know how the Lopital Rule, but I think I will go more uh, deeper, analyze the Lopital Rule. If you want to check using the GeoGebra to check the graph, you can also check and then make sure that you can get also from your calculations. Okay. Yeah, you can check from right here if you want how the graph looks like. And GeoGebra, I'm not sure the apps, but in the if you use desktop or laptop, the graph you can make the three-dimensional graph. Okay. But I think for this semester, just 2 dimensions. It's still okay. Mhm. Can you zoom out, zoom out, zoom out, zoom out? See? Okay, 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 okay. So you can see that the asymptote here, right? Asymptote here. Okay. Yeah, you can also use your laptop if you want to look the graph. Okay. Sometimes it will help you to check whether you are correct or no. Okay. And I think today's class lecture is pretty much better with the all digitals because all the information you need there's actually you can find, right? And then there is always like any info, and even maybe if you feel uh, sometimes you need to review, but maybe you want to review in Chinese, so you can search. I think there are also YouTube channel, right? Like calculus in Chinese. You can take that also as your reference. Okay. Okay. Now, if you look here, we can think the domain first. Okay, we can think the domain. Domain. I think for the domain, remember, uh, if you are looking here, the rational here, so it should be x should be not equal plus minus one, right? Okay, and all x will be included except this one or minus one, and probably that is because both of plus one or minus one is our asymptote, probably, right? And we can see the intercept if there's any. I think the intercept is just 0 and yeah, 0, 0. So the graph should be crossing this point. And if you want to check the asymptote, you can check asymptote. You can check limit as we presume. We can check from 1 and -1. You can check from right, from left, okay? And the functions is 2x squared, x squared minus 1. So it will be having negative and positive infinity, right? Or this is negative. It depends on from where you look at the limit, from left or from right. You can also check the -1 from right or from left, okay? Okay. Maybe sometimes you need to think, okay, how we get this negative and this positive, and how we design or how we design. Imagine, okay, if you think x from the right of 1 or left, just thinking with line number, okay, thinking with line number. If you have 1 here, it's -1. What will be the left of 1? Maybe you can think like maybe 0.99, or from here 1.01, like the small, or maybe 1.1 is also, I think, okay, it's still small. And think, and maybe in your head think what will happen. I think the one that make positive or negative, this one, right? X squared minus 1. If you have anything x maybe 0 point something, if you squared that, maybe it will be a negative, right? If you have from the right, probably it will be positive, right? It will be positive. Same thing happened here, okay? So that you can decide it's positive or negative, okay? Okay, I hope you get my point. Okay, this is for vertical asymptote. So we will have vertical asymptote at x equal 1 and x equal -1. This will be our vertical asymptote. Okay, now the horizontal asymptote we can approach with this infinite limit, positive or negative. Both cases we can try to look at. And then we can check with this, and we know that this will be equal to value 2. So we can think, or we can write y equal to 2 is our horizontal asymptote. And if you want to draw the asymptote first, that is okay. You can draw, and it'll take line, and then the rest we will draw the curve. Okay, we will draw the curve. Okay, first, let me write the functions again. 2x squared, x squared minus 1. Okay, you can do the directly quotient x squared minus 1 squared, and then this will be 4x, x squared minus 1 minus 2x squared, and then 2x. But you can also change this to 2 plus 2 x squared minus 1. Then this is 0 plus using the same quotient, but I think more easier. 0 minus 4x, and directly get minus 4x. Okay, and from here we can set the f prime to be 0, and we are noticed that this 0 is probably our critical. When 4x is 0, then x is 0. So x is 0 will be our critical number. And then we can do some predictions. Okay, some predictions. So this will be 0, and then you have asymptote here, okay, and check the number. So between here, you check -2. This will be positive. F prime is positive. So check on the other value here, also positive. This will be negative. So this will be our maximum value, or local max. 0 will be our local max. Okay, now we are going to look for the second derivative. Okay, let me move to the next page. Move here. Let me write the f prime. We get -4x divided by, okay, f double prime. This, I think, no other way. Okay, we are looking for quotient rule. This become 4. Okay, this become -4 x squared minus 1 squared uh, minus 4x 2 x squared minus 1 2x. Okay, Let me move the x squared minus 1 outside. We have minus 4x squared minus 1 minus 16x squared. Right? X squared. And then we can cancel this with this. This is 3. So we have negative 4. Negative 4. Oh, this should be plus. Should be plus, sorry. Should be plus, negative, negative, sorry. Should be plus. Negative 4 plus 16 is 12 x squared plus 4 divided by x squared minus 1 cubed. My suggestions, okay? If you look here, okay, if you look here, you see that in the quotient rule, sometimes we are having this kind of algebraic formula. Okay. Instead of uh, multiply all the way down, before doing that, look at the common element. We have x squared minus 1, x squared minus 1 here. We can take that out. We can factorize. And it will be more, I think, more simple if you look at this equation. If you try to maybe multiply this x squared and then x squared, and you have x with power of 4. And it will be trouble if you are doing that. And the calculation will be very difficult if you try to do that multiplication. So my suggestions, you can start slowly. Do not rush, multiply everything. Look at the formula first, what you can do, what you can simplify. Like the first derivative, instead of doing quotient rule, maybe you can expand the form, make the separations, and then I think this will be easier to be derived. Okay, so you get this f double prime here. So f double prime is equal to 12x squared plus 4 divided by x squared minus 1 with power of 3. Now the problem is here. What's your conclusions? What is the inflection point? You already see the graph. Is there any inflection point if you see the graph? No, right? That's the conclusion. So if you write here, inflection point is to have if we look at f prime double prime x is 0, then can it be 0 from here? Can x something, some value of x, if you input anything here, it's always squared, always positive. So it means there is no value that f double prime is equal to 0. Okay? So probably there is no inflection point. But what we can do, okay, instead of finding f double prime 0, we can find the interval when concave upwards and concave downwards. That we can do. That way we can do. So first, we can think necessary values of x. For example, the asymptote. Asymptote is at x equal -1 and x equal 1, right? Okay, now we can look for f double prime positive, f double prime negative. Okay, let's start from try 0, okay? Try 0, or try -2 or 2. Oh, so let's try with -2, try 2, try 0. Okay, so let me write here, it's always positive. So because this part always positive, how we decide our x? We decide our x from this, the bottom one. Remember, it has cube. So it may change to negative or it may change to positive. Okay, so this first numerator, we can just expect that it will be positive, right? It's positive, so I will write here. So this will be positive. So we check 0 to here. 0 minus 1, cube, negative, right? Negative. So negative means this will be concave downwards. Okay? And then check negative 2. It's become positive. Minus 1, it's positive. Cube, positive, positive, positive. This is positive. This also 2 will be positive because of squared, x squared minus 1. So x squared makes 2 positive. 4 minus 1, 3. 3 cubed is positive, right? So check negative 2 here. Check 2 also. We get that this 2 area here is positive and also positive. This is upwards and upwards. And then from all this information, okay, can at least imagine roughly sketching the graph. So take this negative 1, negative 1, and then maybe take this as our asymptote here. And then take the maybe around here, this will be another asymptote. Make it a little bit down here. This will be 2. This is 2. Okay. Okay, now what will the graphs look like? Okay. From negative 1 to 1, it should be concave downwards. And you know the intercept is 0, 0. Okay, so we need to draw the intercept here. 0, 0, and it should be maximum value. So it should be maybe like this. Okay, the middle one like this. Okay, now next the other, let me make a little bit higher like that. Okay, another curve. It will start with, you see, this will be concave upwards. This also concave upwards, the left and right part. So it should be like that. So when it's x getting here, it's closer to 2, right? When x is getting negative 1, it's getting here, okay? And the same thing here, the right part, okay? So if I draw the left part, it should be okay. Okay, now that will be our graph. You can maybe write necessary asymptote, like this is y equal to x equal 1, x equal negative 1 asymptote, and then this will be a local max, And you see that this is concave upwards, concave upwards, concave downwards. Okay. Okay, any questions? Any questions? Any questions? Okay. Any question from the online students who are joining online? No? Okay, from classroom? Any question? Any question? So I think the highlight for this problem is this the second derivative here. If you stuck here, what you can do, you can think some interval, okay, and you can check the second derivative. Let's check this second derivative here. Okay. Because some functions they not always having the solution for this f double prime equals 0. Not always the case. Okay. So sometimes you need to think how to draw the concavity. Okay, how to draw a concavity. You need to set up some interval. Okay, I think the best way is look at the asymptote. I think that is easy to follow for drawing the curve. Okay, let me give you another function to think, and maybe you can try at your home, and we can discuss next Thursday. And this will be the end of our lecture. If you have any question, you can write on the chat box for online students. Okay, let me give you the sketch the curve. Okay, this is the functions. Okay, and when you sketch the curve, you can also compare with uh, the graph. Okay, if you want to check the graph first, what's the graph looks like, and then when you calculate, can you make sure or confirm how to make that graph, okay, with your graphing calculator? You can confirm that. And probably a little bit complicated in the middle when you try to derive, but you will actually get the results. You will actually get the results. Okay, if there's no question, we can go to our feedback time. Or if you want to take notes from the previous slides, also okay. If you want from the previous one. Okay. Okay. Any questions? Well, anyway, if you need the QR code, you can scan the QR code here. Okay. Before we start the feedback, if you want. Well, if there is no questions, let me start the feedback. Okay, let me stop the presentation. Okay. Okay. $259. Okay, $259. Okay, get ready. Okay, I will move the slides. Okay, okay, okay. Let me start. 3, 2, 1. Let's go. Okay, I hope this time enough. It's 1 minute, around 1 minute, 20, 30 seconds. Okay, 15 seconds, 15 seconds. Okay, 10 seconds. Okay, random answer, random answer. 3, 2, 1. Okay. Oh, no. Good. Okay, so we learn from our mistake. Okay, we get the good results. Okay, Watson. Is Watson in the classroom? No? Okay. Watson? Who? In the classroom or no? No, right? Okay, let's check another one. Question 2, 3, 2, 1. Okay, let's start. Okay, this should be faster. This should be faster. You can answer faster. Okay, 1 minute, 1 minute. Okay, 40 seconds. Okay, 38, 7. Okay, everyone has voted. Okay, good, 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 good. Okay, good. But I think, okay. Okay, let's go to the next question, last question. Okay, okay, okay. Okay, 3, 2, 1, let's start. You need to do some calculations, but I think there will be, yeah. I hope the time is okay. Oh, very nice, very nice, very nice. Oh, okay. The competition very harsh. Okay, congratulations for the winner. Is the student here, classroom? No? Okay, good, good. Congratulations. Okay, you can collect points and I will give you some presents later. Okay. That will be the end of our course. If you have any questions after the class, you can come to me and we can have some discussion. For online students also, if you have any questions, you can write the question in the chat box. Okay, we can have also discussion if you would like. If not, then you can go out. Okay, class is finished. Okay. Yeah, you're welcome, Rion. Okay, see you soon. See you soon. Yeah, see you everyone.